So we talked about the big pieces of evidence that brought us to the idea of plate tectonics. We start with what they called at the time continental drift, which is the fit of the continents, and the picture on the continents when you put them together, suggesting they used to be together. And then we learn about the ocean floor, what it looks like, what the age of the ocean floor is, and we see this evidence that there's new ocean crust being created in the middle at the mid-ocean ridge, and it slowly pulls apart. So this tells us the story of North and South America pulling away from Africa and Europe. So it kind of completes that picture. So what next? Well, we start looking around the planet for more information. We're now in the late 1950s, early 1960s. We're in the Cold War, and we keep getting more information from the military. In this case, we are very concerned about countries testing nuclear weapons. And when someone tests a nuclear weapon, it creates seismic waves. So if you have a good seismic network, you can detect people setting off or testing nuclear bombs, and you can tell how big the bomb is and where it was located. But as a side benefit for geologists, you get all kinds of information about earthquakes. And this map here from your book shows you not only can you tell where the earthquake was and how big it was, you can even tell how deep it was, and you can start to look for patterns of geologic activity. And what we find is the earthquakes you'll notice on this map are primarily located in very narrow bands. And you'll notice this one running up the middle of the Atlantic Ocean coincides with the location of the mid-ocean ridge and the youngest rocks, which if we dive down to them, we find volcanoes. So we see stuff is going on there. Then we look at the west coast of the United States and South America and the west coast of Central America, and you can see lots of volcanoes focus or earthquakes focused there. But also, if we had a map of volcanoes, we would find those along those same narrow bands. We would find underwater volcanoes along this red stripe going up the middle of the Atlantic Ocean. If we go into Europe, these earthquakes are associated with mountain ranges. If we go to southern Asia, these earthquakes also associated with giant mountain ranges. And then if we go around the Pacific, we find not only volcanoes associated with these earthquakes, but some of the deepest places on the ocean floor, the trenches. So we have lots of geologic activity focused in these very narrow areas. And what we come to understand is that these represent places where plates that make up the Earth's surface are interacting with each other. So if you're in the middle of one of these plates, you might have the occasional earthquake, a little bit of geologic activity. But when you get on the edge of a plate, where one plate meets another, we find all kinds of geologic activity. Earthquakes, volcanoes, mountain ranges, trenches. So that's kind of a confirmation of what we've suspected. The Earth's surface is made up of these giant plates that are moving around, and here's evidence of them interacting with each other. The next thing on our slide here, it says hotspots, and let's take a look at what that means. If we look at the Hawaiian island chain, this is just one example, but a very, very good one, we find that the big island of Hawaii has active volcanoes. Most notably Kilauea, which is erupting right now. There's lava kind of rising up in its caldera. And then Mauna Loa and Mauna Kea, and the big island has a lot of active volcanic activity. If we go to the next island in the chain, Maui, we find volcanoes, but they've been inactive for quite a while. We go to Molokai, volcanoes, but they've been inactive for even longer. We go to Oahu, you can see they're older. Kauai, even older than that. And if we follow the chain up to here, 40 million years ago, and even older as we go farther up the chain. So this is kind of a weird set of volcanoes. The volcanic chains that we looked at here are all active right now. If you look in the Andes Mountains, if you look in the Pacific Northwest of the United States, the Cascades, those volcanoes are all currently active. It's a long chain of volcanoes. The big difference with Hawaii is we've got just a couple active volcanoes and the rest of them are extinct, and they get older as you move farther away from the activity. How do we explain this? Well, we need a heat source for the molten rock, and in this case, that source of molten rock seems to be under the Big Island of Hawaii. But in the past, it was under Maui. And before that, it was under Molokai. And before that, it was under Oahu. So maybe this source of molten rock is moving. Our understanding of how the mantle works, a moving hotspot or a moving source of magma, doesn't make a lot of sense. However, if the plate is moving over that hot spot, then in the past, this part of the plate was over the hot spot, Kauai. The plate moves, that volcano goes dead. And now Oahu is over the hot spot. It forms, it's an active volcano, but the plate keeps moving. It takes Oahu away from the activity. Molokai springs up. It's active for a little while, but it has moved away from the hot spot. Maui is now active. Molokai becomes dormant, and so on until we get to the Big Island of Hawaii. And so here's our picture of what's going on underneath Hawaii right now. It is what we call a relatively stationary hotspot in the mantle, and as the plate moves across that, it keeps burning new holes in the overlying plate. So it's good information. It tells us the plate is moving, and we can also compare time and distance, and we actually can get a rate of plate motion. And it turns out to be a few inches or a few centimeters per year would produce this chain of islands. And that brings another question in our next slide, which is, if we're so clever, can we actually measure this movement? And the answer is yes, we can. Initially, what they did in the 1970s was they set up stations across plate boundaries. So for example, you can see they've got a plate boundary drawn here in California. So you set up on either side of the San Andreas Fault, which represents the boundary between North America and the Pacific Plate. You set up some survey stations and you see, does one move past the other? Because that's what we think is going on at that plate boundary. And it turns out yes. And we can measure that, and you can see the number there is 5.5, and that number is in centimeters per year, so that comes out to about 2 inches a year that those plates are moving past each other. So that was what we did back in the 1970s and 80s. By the late 1980s, early 1990s, we have the global positioning system in place. So we can set up individual stations and see, are those stations moving? And here's the picture that we get. You can see that North America is kind of rotating a little bit. You can see that the Pacific Plate is moving, and the length of the arrow represents how fast the motion is. So the Pacific Plate is moving relatively quickly to the northwest, and that actually matches up with the pattern that we see in the volcanoes on the islands of Hawaii. And not only that, but the rate that we get matches the long-term rate that we got when we looked at the ages of those volcanoes and how far things would have to move over time. We get the same kind of rate, and it comes out to be roughly 9 or 10 centimeters a year, which is about 3 or 4 inches a year. If we want to look at this even more closely, this is a map of the western United States, and you can see that this motion can be quite complex. as the Pacific Ocean goes off to the northwest, it's actually tugging on the western edge of North America and kind of pulling that along with it. When we get to the interior part of the continent, we can see that the actual motion is more straight toward the west. And then you can see that this tugging, because of the connection to the Pacific plate, is causing a little bit of a rotation there. So this is the kind of detail we can get with global positioning systems that confirms the motion of the plates. So the last question we have really with plate tectonics is, what causes this? And so we've got this nice diagram from your book, and it shows the circulation of the Earth's mantle. So at the heart of plate motion is mantle convection. We're heating the mantle up at the core mantle boundary. It rises up toward the surface. In some places that gives us hot spots. In other places that helps drive our mid-ocean ridges. In other places we have the plate sinking back down into the mantle, and we'll talk more about this in the next set of slides where we look specifically at what happens at different plate boundaries. But what you'll notice in terms of activity here is one plate going under another. It's sinking back into the mantle, so that's actually part of the convection. It's cooled enough, and the lithosphere mantle below it, so remember the plates are lithosphere, their crust and then uppermost mantle, that package is now cool enough and dense enough to sink back down into the mantle. It's hot and relatively light when it forms at the mid-ocean ridge, and as it moves away, it cools off and becomes more dense and eventually sinks back down. So this circulation pattern is really what drives the motion of the plates. We kind of put it into three general groups. One group is just the overall convection, and then two specific parts are we're pushing things away from the ridge, which is a little higher, and then we're tugging things down where this plate sinks back into the mantle. The other things you'll notice here is that as this sinks into the mantle, we get some melting, so we get some volcanoes there, and where it sinks into the mantle, there's a deep spot on the ocean floor called the trench that actually marks where the plate is returned to the mantle. So that's our total picture. There's more information, of course, in your textbook, and even more if you were to take physical geology. But that's kind of the general picture of what's going on. And in the next slide set, we'll talk specifically about what happens at different plate boundaries, and we'll take special attention or special time to discuss how ocean crust forms, how continental crust forms, and why the two are different. And we'll talk a little bit about how they behave differently. And then next week, when we do profiles of the Pacific and Atlantic Ocean floor, we'll be able to point to some features that are directly related to plate tectonics.